Good morning, good afternoon, good evening. Thank you for joining us today. I'm Miguel Mendez, Marketing Specialist here at Unravel Data. And before we get started, there are three housekeeping reminders that I would like to cover. The first is, throughout the webinar, please drop your questions into the question box, and we'll do our best to answer them live or respond via email if we're short on time. If you submit one of the top 10 questions during this event as ranked by one of our fantastic panelists, you'll earn some cool Unravel swag. Additionally, this webinar will be available instantly on demand to listen to at your leisure, so feel free to pause or replay as needed. And lastly, help us improve. Share your feedback on the session by rating this webinar, and let us know if there are any other topics you'd like to hear about. All right, that covers it. So with the reminders out of the way, the floor is all yours.
Thank you. Hi, my name is Clinton Ford, VP of Product Marketing at Unravel, and I'm joined today by Don Hilborn, Senior Solutions Engineer at Unravel. Today, we're going to share how you can accelerate performance and reliability using AI that is purpose-built for Databricks. 88% of Databricks users surveyed are turning to AI to improve bug-fixing effectiveness. Why? Well, troubleshooting modern data stacks is typically a toilsome and manual process. The good news, data teams that use DataOps practices and tools will be 10 times more productive, according to Gartner. So here's a look at our agenda. We'll start by taking a look at some of the top challenges to achieving performance and reliability with modern data stacks. Next, we will review the options for data observability and FinOps. Then I'll share an overview of Unravel. At that point, I will hand it over to Don to share Databricks 5 S's and address some of the top questions you've asked leading up to and during this event. So the director of data engineering at a leading producer of flat-rolled aluminum products and the world's largest recycler of aluminum operated dozens of global manufacturing locations, and their ultimate goal was to migrate data analytics for all of their manufacturing plants into the cloud. But they needed cost predictability and to be able to slow the burn. So the director of engineering gathered many of the team members to investigate performance issues, and they were looking through the Unravel recommendations and realized their jobs were not parallelized. The director of engineering started asking who wrote that particular piece of code. Well, it turned out that the director of engineering had written that code, and the director and his team had a good laugh as they realized that even the best experts sometimes make mistakes. 6 months into their 12-month commitment, they were already 80% through the budget. So the director of engineering needed a way to fit more Databricks workloads into the budget. And they aren't alone. Many organizations experience data management challenges, including high cost and low value data integration cycles. Ensuring scalability and performance of their cloud data infrastructure is crucial. For example, a particular query took 28 minutes to complete. It was done on a file scan in Spark, scanning only 10 gigabytes of data, but with over 1 million partitions. Now, these situations aren't unique to this manufacturing company. Many organizations struggle to efficiently and reliably scale their digital infrastructure. The director of engineering realized that open source and cloud native tools could not provide the insights and actionability they needed. This is a common issue as many organizations struggle to detect errors and lower the cost to fix and shorten the resulting downtime. When the director of engineering started to look into the code and issues there, that's where purpose-built AI started to shine. Many organizations have complex, convoluted data pipelines that require toilsome remediation to manage errors. Using data observability and FinOps, the director of engineering and his team were able to resolve data pipeline bottlenecks and achieve the efficiency they needed to quickly deliver value with Databricks across their global manufacturing locations. So companies who buy Unravel often start with homegrown tools, developed in-house, and based on open source software. But these are difficult to use and require a skilled team. As they experience the need for more regular and consistent reporting, they frequently turn to built-in tooling and instrumentation from cloud service and cloud data platform providers. But these tools often lack the granularity needed for data platform showback, chargeback, troubleshooting, and issue resolution. Then, as their cloud usage rapidly expands, they turn to third-party generalist tools, but these typically lack full data stack visibility. And as the data platform grows to support data and AI pipelines and applications, they tend to adopt purpose-built data observability tools to enable productivity, performance, and cost efficiency. So an ideal data observability and FinOps solution enables data teams to achieve performance and reliability. The goal here is to describe your perfect solution and to help guide your choices about which options make the most sense to achieve speed and scale with Databricks. For example, automated job and query performance analysis, out-of-the-box reporting, granular visibility at the cluster, pipeline, job, user, partition, and even code levels, and improving reliability with a single source of truth, automated troubleshooting and SLA management, and end-to-end pipeline visibility. So taking a look at this list, would you agree that these things should be part of the ideal solution? So now let's take a look at what Unravel does. On the left is a representation of your cloud data platform and ecosystem. Unravel ingests telemetry from your stack, then correlates these diverse metadata points into self-service DataOps views and dashboards. Then Unravel's AI Insights engine provides recommendations to optimize performance, allocate costs for showback and chargeback, and provide virtual code reviews integrated into your CI/CD pipelines. Unravel enables you to create guardrails and alerts to notify your team via Slack, email, Teams, and other integrations to help you avoid unpleasant surprises and deliver predictability for your business. So what makes Unravel unique? Well, first of all, is the granularity, the much deeper visibility than a Datadog, for example, because you can go to, Databricks for certain visibility on your jobs and clusters, but not get all of the granular information, about the table, the partitions, the code, the users, and all the DBUs, for example, in one place. Next, that information is, correlated and provides user-level insights, and that is then enables this AI optimization. So AI optimization enables organizations to achieve ideal performance and cost. And I like to use a healthcare analogy. So a lot of tools can show you issues, but none of them can tell you exactly what is best. So for example, like an MRI, you can see exactly what's wrong. So many tools can say, eat healthy, choose, get lots of rest, but they can't necessarily show you the best solution for your acute data pipeline health issues, such as improving performance, making it as good as it possibly can be, or achieving SLAs. And then the third aspect about Unravel that makes it unique is AI optimization that enables predictable spend and financial governance. So now that we have a way to say what best looks like, this enables you to create a predictable outcome. And then it's predictable for two reasons. First of all, if usage patterns change, obviously, usage can go up or down due to workloads, but there can also be waste, right? Anything that is inefficient is just bad, and you need, guardrails to catch those things. And AI optimization gives you visibility into both of these things. I'm also excited to share a new analyst brief written by Nancy Goring, IDC Research Director, Enterprise System Management Observability, and AI Ops Software. As you look for ways to build the business case for your organization to adopt purpose-built AI for data observability and FinOps, this brief provides context for business leaders. For example, this brief defines the key aspects of data observability. And it highlights the role of data observability in enabling AI-driven applications and services. So the director of engineering at the large aluminum producer and recycler leveraged Unravel's AI recommendations to guide the team to success in optimizing cost, performance, and productivity. As a result, they saw a 60% increase in efficiency within just a few weeks. Unravel is the most proven data observability and FinOps platform. We're a member of the FinOps Foundation, named Best Data Tool and Platform of 2023 as part of the annual Cody Awards, named to CRN's Big Data 100 list for the 5th consecutive year, and among the inaugural group of the coolest data observability companies of 2023, a finalist in InfoWorld's Technology of the Year Awards for Cloud Cost Management, and named by Gartner as a sample vendor for both data observability and augmented FinOps. Now it's my pleasure to introduce Don Hilborn, Senior Solutions Engineer at Unravel, to share an overview of the 5 S's for Databricks. Don, over to you.
Hello, everyone. Today we're going to be talking about Spark architecture, as well as optimizing Spark and Databricks Spark. To do that, we're going to look at what we call the 5 S's of distributed compute. These are where you will typically find issues in your Spark environment, and they are spill, skew, storage, shuffle, and serialization. We'll be looking at those a little more depth later. And then finally, we'll wrap up with how we use Unravel's data platform to help us with these issues. So first, let's talk about everything I've learned about Spark in the 9 or 10 years I've been doing it. Well, that would be a lot, but we're actually going to just walk through a fairly simplistic exercise looking at what we would call widgets in a bag of D&D for Don the data guy. And we'll kind of walk that through a fairly typical process that you would do in Spark, but we'll get a look at all those things happening underneath the hood. So first, let's say that I hate gold widgets. I don't want any gold widgets. So can Spark do a good job of filtering those out for me? So probably the way we would divide that work up is to try and look at the bag and divide it into smaller, more edible widgets, if you'd like. And so we kind of break out the Don, the data guy widgets, and we look at the different colors. We recognize that we have a overall set of data here, but there is some differences in the data. And perhaps we can use that to say, for example, remove all the gold widgets because Don, the data guy, doesn't like gold widgets. So to do that, of course, we would just remove those from the bag and we'd be left with those widgets that I do like. But how about if we had to do that, say, in 60 seconds, and perhaps we have millions of bags and billions of gold widgets? Well, that's where a platform like Spark comes in extremely helpful, because what Spark is able to effectively do is very quickly divide this work up into smaller, more manageable parts, distribute that across a cluster, and get your work done in parallel. So, of course, we will take that challenge of removing all gold widgets. We'll try to do so in 60 seconds, and we'll assume that we have a lot of widgets. So, for example, we perhaps have, let's say, 100 different bags of D&Ds, and they're in these crates that are out there waiting to be processed. How can we solve this problem? Well, first, we should look at what resources do we have? What resources are we able to bring together in the cloud environment to solve this problem? And what resources do we need? Can we look at this problem in a way that helps us determine what the resources needed to solve this problem? And of course, that's really where Spark comes in and the Spark architecture comes into play. At its most simplistic level, with data, we're either adding data up, taking averages of data, doing some mathematical function, or we're filtering data. And with Spark, actually filtering data allows us to really see clearly what's happening underneath the hood of the Spark environment. And so as we get into the Spark environment, one of the things that we, of course, want to ask ourselves is, well, where do I start with this problem? How do I break this down into smaller parts and solve this problem that can potentially be millions and millions of crates and billions of bags of Don the data guy widgets? Well, what we do is we actually put to work a cluster. And a cluster is made up of nodes, which are executors, and a node, which is the driver. So we'll talk about that in a little more depth. Like I said, at the end, we'll actually get into the Unravel Data Platform to allow us to really divide this work up. So one of the first things we would want to do is we actually want to divide up the data into smaller, more manageable bags, more manageable crates that we want to work with. Once we have those, we're actually going to call out one of those particular crates, and we'll say, okay, let's tell our cluster here, let's tell our line workers to get to work and let them know, hey, go out there, grab a bag, start processing it. Let's see what you can get done. And the first thing that we do is, like I say, we take one of those crates and we divide it up into smaller pieces of work, manageable packages that our individual cores or processors within our cluster are able to work with, and they're able to do so in parallel. So, of course, we assign each of our bags of widgets a number. And then next, what we want to do is actually assign each of our workers. In this case, workers are really cores. We'll assign each of them a letter, and that allows us to effectively begin to divide up this work among our different cores, CPUs within the nodes within our cluster. So, of course, we assign the work based on the numbers to the cores based on their letters, and everybody goes to work. And we give them the instructions that Brown, the Don data guy, in a pile. Let's process all of them and let's pile them with the others in the corner, for example. So we're just wanting to look at them and do something with them and put them somewhere. And of course, originally, all of our line workers are really given the same amount of work. Why? Because we assume that they're going to be able to process that work in parallel, for the most part, fairly consistent. However, what we see right away is, for whatever reason, it may be the data, it may be the resources, maybe the network, it may be the cloud on that day. Certain cores within our cluster are able to process data more quickly. Not only can they get to the bag, but they can open the bag and start working with the individual widgets and do what we've told them to do, which is to select out some subset of these widgets. And so what we see is that fairly quickly, some of the cores work much faster and others don't. They kind of all work at their own pace. And this is actually very common in a distributed environment for various reasons. But what we need to do is make sure that we're able to take care of that excess capacity that we have, but not overwhelm those cores or those line workers that are currently processing our data. And so what we notice is 4 of our students, our line workers in this case, are idle. And we can potentially assign them additional work. So we basically look at those students or line workers, and we know that they need new tasks. And so we identify the bags of widgets and we assign them to each worker to keep them busy. And this is one of the core functionalities of a distributed system like Spark, is its ability not only to divide your work up initially into a bunch of little packages that can be very easily managed by your student or your line worker, but as that work is being done, being able to continuously add new work to the queue for those students or line workers who aren't busy. Of course, with this, we can continue to work, and some of these line workers will eventually be complete, and others may have a few widgets left to process, but then, of course, eventually they all finish. Given this, there are some core concepts that we just went over that it's probably good to review and understand, and we'll actually be drilling into these throughout the presentation. The first is the concept of the driver. The driver is kind of the teacher, the professor of the classroom, or maybe the shop foreman of the line workers, deciding who gets what work when, and making sure that everybody is busy. The executors are actually the people doing the work. And in this case, we have an executor that, say, has 2 workers, 2 students or line workers on a particular desk where they're doing their work, dividing out these widgets. But there's really one desk for both of them, and that will become important here in just a little bit. But we have, as you saw earlier, we have a couple of workers per desk. Then there's the overall cluster itself. This is really all of the nodes coming together to work as one, and how that's done and how we recognize those different nodes and keep them busy. When it comes to distributed compute and Spark or Databricks Spark, Apache Spark, slots, cores, and threads are pretty much synonymous. That's not necessarily always the case, but I do want to indicate that we're going to kind of oversimplify here. And really, a slot or a core or a thread, that's within our CPU. We have a core. Some CPUs have 4 or 8, 16 cores. Through each of those, we can process only one thread at a time. And in Spark, whether it be Apache Spark or Databricks Spark, a thread is really the lowest granularity of an instruction. And we'll see that a little bit later, where we see stages are made up of threads and jobs are made up of stages. And the thread itself is where we assign tasks to be done. And we want to make sure that we're using all of those that we have within our environment as optimally as possible, because that's the cost for us in the cloud world. The other thing that's worth noting is these nodes, they share resources. And in some cases, the cluster itself, the driver, will also share resources. So we've got to take that into account when we're building the work that we're going to give to these line workers and how we're dividing up that work so that it can take full advantage of our cluster. One of the things that we'll do in order to take full advantage is this concept of parallelization. And as you saw earlier, that really is making sure that I'm giving each of my line workers, each of my students, a task to do that they can do in parallel. They're not waiting for the other student or the other line worker in order for them to finish their task. They can finish it and move on to the next task. You will see in Databricks Spark, Apache Spark, that for the most part, stages have to complete before the next stage can begin. So in a stage, you'll have multiple tasks. If you have a long-running task, it's going to have to complete generally. With Spark 3.0, there are some exceptions, but generally it's going to have to complete before the job can move on to the next stage. And of course, a job is comprised of multiple stages. Another way that we divide up our work is with partitions. It's important to note that there's partitions on how the data is stored. So how do we divide up the data across our storage? But that same technique is used while the data is being processed as well. So is our data partitioned in such a way that we can make the most use of our processors? And we'll see, as we talked about in the beginning with the 5 S's, if we don't do that well, we will encounter skew, and skew can introduce its own set of problems. As I mentioned, there are jobs, stages, and tasks, and that's really the hierarchy within Apache Spark and Databricks Spark. Is you create a job, which is a body of work that you want to get done. Spark breaks that into stages and then breaks that into tasks, and you kind of work up the hierarchy from there. Like I mentioned earlier, generally a stage will have to finish before the next stage will begin. So let's talk a little bit about the cluster. And first, we talked a little bit about the driver. They're kind of the wizard of the classroom if you're into Harry Potter, or they're the foreman of your line workers if you're into manufacturing cars or something. And that is really the role of the driver. They really decide who gets what work when, and when people finish their work, they may report that back to the driver, where the driver can actually use that in future steps. But this is kind of the conductor. This is the person, or the node in this case, that's in control. We also have the executors. And of course, this is where the work happens. This is where the driver tells them what data they're to process and how they're to process that data. Typically, we have one driver and numerous executors. Often when auto scaling or other scaling capabilities are introduced, we may have multiple executors. In this case, we have 6, we could have 12, we could have 24, and we could scale as the work dictates that we need to. Now, of course, all this really comes together to form what we call the cluster. And this is a body of nodes, one driver and one or more executors working together in tangent to work through some set of data, pretty much in the way we've discussed thus far. Like I said, you can filter, you can edge, you can average, but there's this body of work that's distributed across the executors and the driver is in control of it, and that comprises our cluster, and that's where the work is really done. Now, as I mentioned earlier, for us, slots, thread, cores, they're really interchangeable terms. And what we mean by that is that's one of these little robot guys that's either A or B or G or H in this case. There are core, and a task will be processed at that level. You'll notice that a node is actually comprised of more than one core, and it can be 2, it can be 4. Again, it can get some of these nodes get very large, but the concept to take away is that one and only one core is what's needed to process a thread. And that in Spark is a task. That's kind of the lowest level of work. And that's the work that actually happens on the machine. You heard earlier, I mentioned this concept of shared resources across nodes, and that's important because they do. This is a single node within the cloud. Of course, the hardware in the cloud is virtual, and so this is a virtual node, if you will, but it still is sharing critical resources. In this case, RAM, disk, and even the network. So as these nodes need to speak with each other, that data may travel across the backbone of a particular environment or even the network of a particular environment. And that is shuffle. That's where each node is writing out its results and sharing it with another node. And that's where the network would become critical. What you see is in this particular situation, we've got a max parallelization of 12 tasks, for example. So we've got 6 executors, 2 cores each. We can do 12 things simultaneously. And that becomes very important, especially as you'll see later as we get into Unravel, being able to look at each of those tasks, each of those cores, and see, are they actually running in parallel? Do we have some long running threads? If so, why? Is that something that we can ultimately address? It's also worth noting that we have this concept of a data set, and that becomes significant in a couple of ways. Generally, anytime we run into an issue in our distributed environment, it's going to be in one of 3 areas. It's going to be in the data set itself, how the data set is organized, how it's partitioned, how big is it? Does it have a small file issue where it's a bunch of very small files? All that comes into play. That's really the storage. Then the other is the resources themselves. Do we have enough nodes? Do we have enough cores? Do we have enough memory to handle all the processing that we're trying to do? Do we have enough bandwidth in the network to move data around? And then finally is the code itself. Is the code efficient? Is it reading the data in parallel? Is it processing it in parallel? Is it writing it out in parallel? Is it gathering all the data together in the driver for some reason and doing a bunch of processing there? If so, is that something that actually needs to be done, or could we look at distributing that across the environment? This, of course, goes to partitions. As I was speaking of earlier, ideally, we want to partition our data to go grab our data in such a way that it can be evenly distributed across our cluster. All of this comes together to be a Spark job. In this case, we'll say with a very simplistic stage. And this is your instruction. Go eliminate all brown widgets and pile the rest of them in a corner, kind of what we saw earlier. So let's talk a little bit more about some of these distributed concepts and how they help us solve our problems, especially in the big data world. So what's the relationship between applications, jobs, stages, and tasks? Well, we spoke about this a little earlier, right? The job is what you would schedule in Databricks and Spark. It's going to be broken down into stages. Those stages will be broken down into tasks. An application itself can actually be comprised of more than one job. So you might define an application that requires 7 different jobs to complete. In some cases, some of them running in parallel, but it'll always go through that hierarchy where the application is made up of multiple jobs, a job is made up of multiple stages, and a stage is made up of multiple tasks. And really, it's the task is the only thing that runs on the cluster. Everything else is an abstraction level. So we talked about that. Now let's look into how each task knows what piece of data it's supposed to process. And as you might imagine, that's going to come down to the driver. The driver is going to assign that and ultimately keep track of whether or not that work is done. And that's really the whole role of the driver. So in this case, let's say we have 3 executors with 2 slots. Well, of course, we can process in parallel 6 tasks. And that's important as you're sizing your cluster and trying to understand just how big your cluster should be. So let's look next at what component decides how to partition the data and how it should be distributed. Well, of course, that is the driver ultimately, but we're also going to see that a task is executed in one of these slots, one of these robots that you see here. And again, if we think back to that hierarchy, we can determine, okay, given this cluster size, I should have 12 tasks running at any given time, if at all possible. So let's talk a little bit about how the environment and tasks are executed. Basically, what we'll see is that the driver itself will determine that it wants a particular node to process a particular set of data. That node in Spark is a single Java virtual machine. This is important because some platforms out there like Hadoop will have more than one JVM per node potentially, and this introduces its own set of complexities. But in the Spark world, you only need to be concerned with a single Java virtual machine, which is an abstraction level running on that node, and therefore contention and other things are easier to manage than they would be, say, in a Hadoop environment. All right, so let's now drill into, and we're quickly going to get into Unravel to see how we address these, but let's look at those 5 S's. What are the problems that we can encounter when processing big data using a distributed environment like Spark? And one of them is serialization. And very simplistically, serialization is where the machine, the computer, takes machine code, if you will. It takes the data that's organized in a specific way for the processing that's being done against it, and it has to reserialize that data for processing to be done in another application in another thread. And that is costly within a distributed environment. And that typically happens most frequently in what are called user-defined functions. So at its core, Spark is written in Scala ultimately. And so when you create a user-defined function, say in Python, where you've actually written the code that is performing against the data, it's going to have to be deserialized and reserialized for Python. And then after the function is applied, it's going to have to be deserialized and reserialized for Scala or for the underlying API. So in this situation, you're encouraged to use native functions wherever possible because it will prevent that from occurring. There are other things that serialization do that just aren't good. One of them is it really becomes an analysis barrier to one of the optimizers, the Catalyst optimizer, that is built into Spark. And it really can't connect to the code before and after the UDF in order to optimize it. And so if at all possible, you should stay away from UDFs. Are there times when there's not a native function that you can use? Yes, and you just have to take the hit at that time. But you should always first investigate, is there some existing functionality out there, an existing function or combination of that I can use to get done what I want to get done? And if so, I would use that. As I mentioned earlier, there's various serialization and deserialization that goes on depending on your code and depending on your business logic. But in general, you want to avoid that. Now, skew is a matter of your data or your processing being askew, if you will, meaning that your data potentially has some subset that is much larger than the other subsets, or your processing of certain data is much more intensive than it is of other data. And that gives you skew. And of course, that really doesn't fully utilize your distributed cluster, your Spark or Databricks Spark cluster. And so some ways that you can address that is making sure, for example, that your partitions are sized the way data is typically read. So data is typically read in 128 megabyte partitions. And so try to organize your data where each read is full, or you don't want it to do a read looking for 128 megabytes and grab much less data. I use the analogy of when I was moving out of college to my first apartment, it was more than sufficient for my friend to show up in his Ford F-150. We loaded some things in the back and we were done. When I was later moving my 4 children, wife, dog, and neighbors in some cases across country, a tractor trailer was much more effective. The point being, you really want to make sure that you choose the right size vehicle, the right size partitioning for your data, and vice versa. You don't want to go to all the overhead of getting the tractor trailer if you're just moving a single dorm room. Also, you don't want to use an F-150 to move yourself across country because you're going to make a lot of trips. And so try to avoid skew from that perspective. And there's ways you can do that. There's this concept of salting, where basically you artificially introduce into the skew data a number that can be used to distribute it more evenly. There's also hints that you can add. In some cases, these hints are proprietary to Databricks, but there are hints you can add from a key perspective that allow you to more easily and evenly distribute the data. And then we have this concept of adaptive skew join, which really came into existence with Spark 3.1, and that's another way that you can address skew. Now let's look real quickly at spill. With spill, what happens is one of those nodes that we were talking about earlier has some amount of RAM or memory. It's taken on so many different names, but there's some availability of memory. That memory that is stored electrically, and it is extremely accessible to the CPU because it's electrons traveling across your bus in your virtual environment. When spill happens, that means that that memory is typically, it overflows and it's going to go to whatever your disk is that you have associated with that node. So in the case of if you have an SSD, well, that's not too bad. It's not going to be as fast as being in memory, but it's not a spinning disk with a read-write head. So it's going to be somewhat more efficient. And then you see a degradation from there down, where if you are spilling to disk that has a read-write head and a spinning metal disk, it's going to be more costly to deal with that data and the spill that's going on. It could potentially even destabilize your job, where eventually it fails or runs into errors. And so the way you want to address this is you want to avoid it, if at all possible, at all costs. As I mentioned, for example, you can run into out-of-memory errors with this, which may cause your job to fail. It certainly will impact the performance of your job and may cause it to run longer than what is acceptable in the SLA. And so there's lots of ramifications to spill. Ideally, you want to avoid it. Here are some ways you can. You can adjust the size of your shuffle partitions. And that's one of the things you're going to see with our 5S's is there's really a symbiotic as well as interdependency type relationship where one is dependent on the other and vice versa, and a change in one may improve or worsen another, and you're kind of constantly balancing that. But here are some techniques to avoid it. You can use a join, but you don't want to use a cross join. You can use what's called a broadcast join, which basically takes the smaller table and broadcasts it to the larger table, so there's not the back and forth as it's bringing the keys together for the join. And then, of course, one of the things you have to look at when it comes to spill is memory itself. Do you have enough memory? Should you allocate instances with more memory? And do you have enough disk? What disk do you have? Like I said earlier, if you have SSD or something that's really still electronic, it may not be memory, but it's not a physically spinning disk with a read-write head. Well, you may not encounter as many issues, and maybe you're willing to have that trade-off to keep cost of your cluster down. And these are some settings that you can look at to mitigate spill. As I mentioned earlier, how is the data partitioned? Do you repartition the data before you process it? Is it being read in a way that's very efficient, but it really needs to be repartitioned before you process it? Look at the bytes actually being processed. How many of your overall tasks are encountering spill? Because it's a balancing game. It's going to be cost. It's going to be, am I willing to change the code? Am I willing to change the data? And if you have 800 tasks processing without spill, and say 50 of them are, the impact may be minimal, and you may decide, really, I don't need to mitigate that spill. It's just going to be too costly if I try to do so. Let's look at shuffles. And as I said earlier, really, shuffles are just where the individual nodes are required to share information with each other. I like to explain this with kind of an analogy that I use to explain what's known as the CAP theorem. The CAP theorem, CAP, stands for a problem that you will incur whenever you start to do distributed compute. So the example is, let's say that I choose to start a company. The whole business of the company is that people call me and tell me something to remember. Then when they call me back, they tell me their name and address, and I tell them what I remembered for them. Business is so good, I start my new business out that I can't handle all the calls coming in. So I decide to hire a worker that is going to take calls on another line, and all is great. I basically am able to double the number of customers that I'm able to handle, until one day Joe Smith calls me and says, Don, do you remember my wife's birthday? Here's my address. And I say, I don't have anything about your wife's birthday. And of course, he hangs up, never to use the service again, bad mouthing us everywhere. It's a horrible service. What went wrong? Well, we encountered the first issue that you encounter when you are doing distributed compute, and that's the C in CAP, which stands for consistency. And so the fact that me and my partner are taking different calls and writing down different things, we're not in sync. To be in sync, we actually have to introduce the second part of CAP theorem, the A, which is availability. We're going to have to stop periodically and sync our journals. And while we're doing that, we won't be able to take future calls. And it's really that balance that you're continuously working with, as well as the final, the P part of CAP theorem, which is my partner, we're doing so well, he decides he's going to move to Cancun and never work again. I've encountered the third part of CAP, which is partition tolerance, which means what happens when I lose a node, right? I lose some data from a node. How do I handle that? And typically that's done with concepts like write-ahead logs and other caching concepts, so that when they go to Cancun, you still have something left of what they were processing, and you know where they were in the queue of processing it, so you can hire someone else to take on that processing and get you in sync. And so what you're seeing here is some things that cause what are known as wide transformations. In Databricks, Spark, or Apache Spark, or really any distributed system in the cloud for that matter, you have what are known as wide transformations versus narrow transformations. Wide transformations require you to do that shuffle. What does that mean? That means that your different nodes need to know information about each other in order to do the work, and therefore they shuffle, they write that out so that the other node can read it in. And these, of course, are joins where you might have different data from different tables. Distinct, where you're trying to look at what are the unique records across all of these nodes, grouping by particular records, or sorting, doing an order by. There are some options to explore when it comes to optimizing joins. The reordering of the joins, get rid of as much data as you can early on. Bucketing is a contentious topic. It can be done. It's extremely difficult, and probably most people should not be doing bucketing, but if you know what you're doing, it can help. I mentioned the broadcast hash join earlier. This is where we simply take the smaller table and broadcast its keys that we're doing a join on to the larger table, and then that way there's not the back and forth as it's actually doing that join. With Photon, you have this concept of shuffle hash joins. This is the default, and so it's really kind of doing a combination not only of the hash join, but trying to order them in such a way where it knows when it hits the next join as it's going down the list, that because they're ordered, it doesn't have to go back up and say, or go down further to say, wait, is there another match? No, these have been hashed and shuffled in such a way that you don't have to do that. And then, of course, the sort merge join, which is the default for Spark, is very similar, where you're first sorting each and then you bring them together, again, knowing that they're ordered in such a way that you don't have to keep going up and down the list to see whether or not you have a match. There's lots of different problems that can be brought on by these. Of course, the goal is minimize shuffle when possible. Use Databricks automated query engine. It's cost-based optimizer. Those are built in. Try to make sure that you're getting the full advantage of them. Like I said earlier, by perhaps not using black boxes of UDFs and other things. And then, of course, there's properties that you can actually set to address this. Finally, we just have to be pragmatic with shuffles, right? Is they are going to happen. Our nodes cannot operate autonomously forever. So we just need to accept that they're going to happen. We want them to be with as little data as possible, as infrequently as possible, but they're going to happen. And some of them actually happen quite fast. It's part of what these distributed systems are good at. You do have issues with what's called the small file problem or tiny files. And there's other issues that you may encounter in the data itself that introduces shuffles where, again, you might be able to do something upstream, bringing that data together, doing optimize with Delta so you don't incur the small file problem. Some other mitigation we talked about is what's your disk? Is it the most performant disk you can get? Are you sorting columns or dealing with data that you don't really need? Get that data out as early as possible. Flatten out or denormalize your data sets. This is going to help reduce the number of joins, especially when we're using columnar tables and a columnar engine like Photon, and then make sure that you have a good join strategy. Join may not always be the best option if you look at the data holistically. So let's look at we looked at optimizing joins from a bucketing perspective. Like I said, bucketing is really something I would stay away from unless you know what you're doing. And of course, it doesn't even become a factor if you're dealing with data of less than 1 to 5 terabytes, depending on the data. So stay away from it if at all possible. We did talk about the broadcast hash joining, how it works, how the tables are reassembled, and then ultimately how we're able to use those reassembled data for each executor, basically using our underlying infrastructure optimally. But just know that sometimes broadcast tables themselves can be very large, and that's okay. You have to really look, it's always a trade-off is, should I broadcast this? Is it small enough that I can broadcast it and get value? Or is it too big, and by broadcasting it, I may actually slow everything down? And that's just one of those things that you develop with experience and understanding your data. This is kind of a evolution of the sort merge join that we talked about and how that works. Generally, it's slower actually than the hash join, but there are some value aspects of it where it takes less time to create the hash. Both scenarios can still shuffle data, so you're not always winning, say, with the sort merge or the hash join, either one. It really comes down to your insight into the data and the processing, and of course, optimizing that. So with that, I will close. Thank you very much. Hopefully this has been helpful, and sign up for our Unravel free version, and you can experience a lot of this yourself.
Thank you, Don. Now let's take a look at some of the questions that have been coming in. Really appreciate all those questions you've entered, and feel free to add your question into the Q&A box, and we'll answer as many of those as we have time. Okay, so first question, how is your product different from Lakehouse IQ that offers a Copilot experience? Well, the main difference between many code generation products currently available is that they are typically based on static code analysis. While Unravel's AI Insights engine uses dynamic code analysis, meaning that its review of code and SQL, Python, Scala is based on more than just the code itself, but also the data layout, the table structure, partitioning, and other metadata. Unravel also analyzes your code's runtime performance and efficiency to enhance the recommendations. Okay, here's another question. Can this solution combine AWS and Databricks observability FinOps? Well, Unravel provides observability for a variety of cloud data platforms, including Databricks, Snowflake, BigQuery, Amazon EMR, and more. Feel free to reach out with your specific needs, and we'd be happy to provide a demo of how you can leverage Unravel for your data analytics with Databricks on AWS. Okay, here's another question. What type of data does Unravel store or collect from the users? Is only metadata that needed? Yes, so we only collect performance and telemetry data from the data application jobs themselves. So we do not have access to the data stored in your data lake or in other databases. And that data is not and cannot be shared with Unravel. Okay, another question. What is the data governance model in Unravel? So Unravel is committed to security and focused on keeping our clients and their data safe. The solution designed by Unravel manages customer data based on the 5 SOC trust services criteria. So security, availability, processing integrity, confidentiality, and privacy. So we use TLS encryption, the same standard used by secure websites to secure data in transit and at rest. Unravel is SOC 2 compliant, and it has earned a Service Organization Control, or SOC 2 Type 2 certification. And feel free to reach out if you have questions. Just reply to the email for this webinar. Happy to send you a link to some documentation for that. Okay, and another question that came in, is Unravel offered as a pay-as-you-go model? Yes, Unravel for Databricks is available in a standard or free tier, which is free forever, and then also as a pay-as-you-go model. So you can learn more about this at unraveldata.com/pricing. All right, so if we didn't get to your question in the chat, we'll try to respond via email right after this event. Feel free to reach out to us. And then if you're ready to see how much more performance, productivity, and efficiency you can achieve, go ahead and request a free Unravel account for Databricks at unraveldata.com/create-account and experience the benefits for yourself. Thank you so much for joining us today.